Why doesn't it topple over? There's a net torque on it, so we might think it should. So imagine when it's leaning on the side there should be a force from weight pulling it down, topple it over, but it doesn't. Why does this figure skater, when she pulls her arms in, why does she start to spin faster? There's no external torque on her, so how do we explain it? Here's another example of something that's not toppling over. Look at this motorcycle rider. I mean, he's way over like this, and she's not toppling over. I mean, there's barely enough space in between. It's very similar to the top reason. So all of these phenomena are explained through angular momentum. And that's what we're looking at next. So we know momentum is mass times velocity. What might we see as the angular equivalent to this? Well, we're going to say angular momentum. We're going to use the letter L for this. I hope that it makes sense that it would be some angular equivalent. So instead of mass, it's probably inertia. Instead of velocity, it's probably angular velocity. And it is. The direction of the angular momentum is given by the right-hand rule. So if you grab the axis with your right hand so that the fingers curl around in the direction of spin, the thumb points along the axis in the direction of the angular quantity. We also had the equation that the force is the time derivative of the momentum. Well, same thing for torque. Torque is going to be the time derivative of the angular momentum. All the linear equations, and now the angular equations. And you'll notice that they're very similar to our linear equations. So the ones we really need to make sure we understand is the ones that go between linear quantities and angular quantities. Then that's the ones here in the middle. And we haven't added to that at all. So let's look at a situation where we have this clay ball coming in and hitting this rod that's fixed about the center here. Let's figure out what the angular speed of this system would be. And notice it gets stuck to it. So there's an external force occurring at the pivot, so linear momentum will not be conserved for this system of the clay ball and this rod. But there's no external torque, so the L would be conserved. So there is a force at the pivot point, but the distance between that force and the pivot point is 0, so there's no external torque on this system of the clay ball and the rod. So angular momentum must be conserved. So that means Li must be equal to Lf. Well, Lf would be the rotational inertia of the point particle plus the rotational inertia of the rod times omega final. How would we figure out what the initial angular momentum is? Well, again, that's going to be equal to I omega, but remember that omega is equal to V over R, and I would be mr squared. So the r's cancel and we're left with mrv. R is going to be the distance between that motion that was moving along that dotted line and the pivot point. So that's going to be 0.3 meters. That's how far away that clay ball hit from the pivot point. So if you take the mass, 1 times 6.6 times 0.3 meters, you get 1.98. On the right-hand side, the mass, the rotational inertia of the clay ball would be mr squared, which would be 1 times 0.3 squared, plus 1/12 ml squared. That's the rotational inertia of a rod about the center. The mass of the rod is 10 kilograms, and the length of it is 0.8. So we can plug in. And when we do, simplify it, we can solve for omega, and we get 3.18 radians per second. That's how fast it's spinning right now. Let's look at another example for angular momentum. So we have this disc that's spinning around at 5 radians per second, and we're going to drop this clay ball straight down on top of it. Let's figure out what its new angular speed would be. It's going to have conservation of angular momentum because there's no external torque. There are external forces acting on it at the pivot, and there's gravity force acting on this, but so there it means there's no linear momentum not conserved. So Pi does not equal P final. You can see the ball is no longer moving, but angular momentum is still conserved because there's no external torque. So Li equals Lf. So at first, the only thing it was spinning was the disk. So that would be the rotational inertia of the cylinder, the disk, times its initial angular velocity. And that's going to be equal to the combined rotational inertia of the point mass and the cylinder combined times the final angular speed. So the rotational inertia of the disk is given as 1/2 mr squared. We know the mass is 20 kilograms. We know r is 0.4. For the rotational inertia at the end, it's going to be mr squared for the clay ball, which is 1 kilogram, times its distance away, which is 0.3 squared, plus 1/2 mr squared, which is the same for the disk again. Given what our initial angular velocity was, and plugging in all the numbers that we know, we get 8 on the left-hand side. And the right-hand side, we can simplify and solve for omega f, and we get 4.73. Actually, I kind of forget what the initial angular velocity was. Oh, it's 5. There we go. 5. And we can see the final is 4.73, so it's a little bit slower. All right, now we're going to look at the following system. We've got these masses that are 0.3 meters away from the center. There's 4 of them. The initial angular velocity is 1.3 radians per second. And now they're going to move in. So it's similar to if we have kids on a merry-go-round and they start at the outside and they work their way inward. What happens? There's, again, no external torque. It's all the forces are between the clay balls and the disc. Those are only internal forces. There's no external torque. So that means the initial and final angular momentum are conserved, or the same. In the beginning, it's 4 times the rotational inertia of one mass of clay ball going around, plus the rotational inertia of the cylinder, times the initial angular velocity, which I think was 1.3 radians per second. And that's going to be equal to the rotational inertia of the system times the final angular velocity at the very end. The reason I'm putting a prime there is because they moved inward, so the rotational inertia of one point mass is different now. Find the rotational inertia of one point mass, it'd be mr squared, so 4 times that would give us all 4. For the cylinder, it's 1/2 mr squared. And then at the end, when they moved in, I'm using r prime because it's now, instead of being 0.3 meters, now it's 0.2 meters. I could plug in the numbers because I know the masses, I know r, I know what the initial velocity, angular velocity was 1.3. I can solve for the final, and I get 1.45 radians per second. So it sped up and went faster. All right, let's look at another one. What is the final translational and angular speeds of the system? Okay, for this one, we can see that it's not fixed. I'm showing the center mass, but that's or the center of the rod, but it's not fixed. It can actually slide. So this would be like a top-down view looking at an ice skater, and they're going to hit a log. And it's slick on this lake or on this river, and they're going to go sliding off together. Afterwards, you notice that the center of mass of the system moves up towards it. That's the blue point. And notice it's going straight across. We've got the initial velocity 6.6. We know all the dimensions. We know the masses. Well, there's no external force. So that means linear momentum is conserved. There's also no external torques, which means angular momentum is conserved. So Pi equals Pf. Initially, it's just the 1 kilogram moving at 6.6 meters per second. That would be the left-hand side. And afterwards, it's going to be the 1 kilogram plus the 10 kilograms moving together. And that would be times the velocity of the center of mass. And so I can solve this for the velocity of the center of mass. Afterwards, that's the blue dot, and that's 0.6 meters per second that we saw going in a straight line. We also know the initial angular momentum has to be equal to the final angular momentum. So the initial angular momentum would be, again, mr squared times omega. That would be I omega. But omega is equal to V over R, so the R's cancel and we just have mRV. Now, you'll notice that I have R prime of the center mass. That's how far it was from the center of mass. Remember, that's where that blue dot shifted. And then on the right-hand side, I have the I of the point particle and the I of the rod. And both of those are also going to be dependent upon where that center mass is. So I'm going to flip back here so you can see that blue dot again. See that blue dot shifts up. I have to figure out what the center mass of the whole system is. So I'm going to have to go back and use my ideas for figuring out the center mass to figure out where that point is before I can really solve this problem. The rotational inertia of the point mass afterwards is just simply going to be mr squared. And then for the rod, it's going to be using a parallel axis theorem, ICM plus md squared. The ICM for this rod is, of course, 112 ml squared. In order to figure out the center mass in the vertical and the y direction, that's where that blue dot was. Let's say where that black point was, let's say that's where the origin is. Let me come all the way back to my picture here. Let's put our origin right here. And so when this hits, its y position would be 0.3 meters away. The y position for the center mass of the rod is at 0. All right, let me fast forward a little bit. So that means finding the center of mass would be 1 times 0.3 plus 10 times 0, all of that divided by the total mass, which is 11. And so I get the y position of the center mass to be 0.0273. Well, that's how much it's from 0. So in other words, that's how far it shifts up from that black dot at the very beginning. 0.3 away from this. So if I take 0.3 minus the 0.0273, I get 0.273. A little bit more than that, but I get 0.273. That would be the new distance the clay is from that blue dot. So I'm going to back up again. So I'm going to back up so you can see that again. So think about where this hits, which would be right about here, and that blue dot is right about here. So that's going to be 0.273 in between them, right about there. All right. Okay, so now I can use this 0.273 and plug that in and solve this. So on the left-hand side, the mass of 1 times the 0.273 times 6.6, I get 1.8. And the mr prime squared, I get 0.074. And then I have 1/12 ml squared plus md squared. The d is a shift of 0.0273. So we have to be careful. The d is going to be 0.0273. So I can plug in my numbers. For the mass would be 10. The length was 0.8, that's L. And now we can solve for omega f. We end up getting 2.93 radians per second. So we found the velocity of the center of mass, and we figured out what the angular speed of that thing rotating is. Now let's look at one final situation. This is an elastic collision. So we want to find the final translational and angular speeds of the rod and mass. So in this situation, this is also going to be able to slide off. We're going to have three things that are conserved. We're going to have momentums conserved, linear momentum. We're going to have angular momentums conserved, and we're going to have the kinetic energy being held constant because it's an elastic collision. So the reason why that the linear momentum is conserved is because there's no external forces, only forces between the rod and the ball. And the reason why there's the angular momentum is conserved is because there's no external torques. It's only the forces between the ball and the rod that causes rotation. And so that's what it would look like. So let's look at this. Pi would be equal to Pf. And so initially it just has a mass of 1 kilogram times the initial velocity. I think that was 6.6 if I remember correctly. And then afterwards the mass goes flying off the other direction of 1 kilogram, and the rod itself has a mass of 10 kilograms. So there's two unknowns here. We don't know the final velocity of the ball as it bounces back the opposite direction, and we don't know the velocity of the center of mass. Also, using Li equals Lf, what's nice about this one is that the R does not change, so we don't have to find the center of mass. Doesn't really change for this, its position, and so the R is the same. And so we can plug in the mass, we can plug in the velocity on the left-hand side and the R, which is 0.3. And the right-hand side, it'd be mass of 1, and the R again is 0.3. And so it looks like this. We don't know what the final angular, or we don't know what the final velocity is. For the rod, it's going to be 1/12 ml squared omega. Omega is going to be equal to the velocity of the center of mass divided by R, where R is 1/2 the length. I can plug in the mass of 10. I can plug in the length, and it simplifies to the following there. So I didn't plug in the V over R, but I could have simplified it in terms of VCM. Okay. For the kinetic energy, the initial must be equal to the final. So we have 1/2 m times v squared, and that's going to be equal to 1/2 mvf squared plus the translational kinetic energy of the center of mass of the rod plus its rotational kinetic energy, because it's both translating and rotating. And so I can go ahead and plug into this and simplify it, and I've got the following. So I have three unknowns. I've got the velocity, final velocity of the ball as it bounces back. I have the velocity of the center of mass, and I have the angular velocity of the rod. But I also have three equations. I have the kinetic energy equation, I have the angular momentum equation, and I have the linear momentum equation. And I can solve this systems of equations. I'm taking the second equation and I'm solving it for velocity of the center of mass in terms of everything else. And I took the last equation and solved it for omega in terms of everything else. And I can go ahead and plug into that. And notice everything then will be in terms of final velocity. And this is what I end up getting. I get the final velocity to be either 6.6 meters per second or negative 3.8 meters per second, because it's a quadratic. Well, I hope that it doesn't make sense of 6.6. It doesn't go through the rod. It bounces back, so it must be the negative 3.8. I can plug that into the first equation to figure out the center of mass velocity. What's either going to be 0 or 1.04. Only thing that makes sense is 1.04. And I can plug that in to the second equation to figure out the angular velocity. It's either 0 or 5.85. So the only one that makes sense is 5.85. And so those are my answers. So if you remember, we had these spinning objects, and we wondered, why doesn't the topple over? Why doesn't this motorcycle topple over? Why is it this skater is able to spin faster? In both of these, we have angular, in all three of these, we have angular momentums conserved. And then for these two on the left, the reason why it doesn't topple over is because it's also a vector quantity, this idea of angular momentum. So using the right-hand rule for this top, its vector points upward for the top. And for the motorcyclist, we have to look at which direction the wheels are spinning, and they're probably coming towards us here, which means if you use the right-hand rule, curling your fingers around in the direction of the tire spinning, the momentum vector is kind of pointing upward at an angle this direction. Well, it takes a torque to get that to topple over. And even though there is this torque that's acting on this weight, instead of toppling over, what happens is it precesses. It kind of spins around, kind of like the top was doing. It's kind of precessing around, and so that's what happens. Well, this bicyclist precesses around. That's exactly what we wanted to do.